Our next speaker, Tobia Marcucci, is a professor at UC Santa Barbara. Did his PhD at MIT and did a number of visiting scholar positions here at Stanford as part of that. Generally, I will personally say that graph of convex sets is to me one of the most interesting things that has happened in kind of the theory and applications of convex optimization in the last 10 years. And so I'm super enthusiastic to introduce him for what I'm sure is going to be a great talk. Thank you.
Okay, can you hear me online? I guess so. Well, thank you so much, Parth, for the very nice introduction. As Parth anticipated, I would like today to take this opportunity to give you a quick tutorial on these graphs of convex sets, which has been the focus of my PhD and also now of my beginning of a faculty trajectory. I would like also to take the time to present a little bit of this GCSOPT library, which is a CVXPY based library for solving these graph of convex sets optimization problems. So this is the outline of my presentation today. I will start by telling you what these graphs of convex sets are and what kind of optimization problems we can solve over these kind of data structures. Then I will quickly dive a little bit into how we can solve these GCS problems and what are the optimization techniques that we use. Then I will give you an overview of examples and applications of this machinery, mostly coming from robotics, and then a quick highlight of the main features of this GCSOPT library for solving these GCS problems. So I'm sure that everybody in this room is familiar with ordinary weighted graphs. They can be directed or undirected, and we have costs that are scalars that are associated with the vertices and the edges of a graph. A graph of convex sets generalizes the notion of an ordinary weighted graph as follows. In a GCS, the weights on the vertices and the edges of the graph are not even scalars anymore, but they depend on underlying convex optimization problems. So specifically, every vertex in a GCS is paired with a convex program that is defined by three objects. A continuous variable is lowercase xv. Then we have a convex constraint of this form, defined by the set calligraphic xv. And then we have a convex objective function, f of v, that given the value of the continuous variables, returns the weight of the vertex. Okay. Similarly, on the edges of a GCS, we have convex constraints and convex functions. So if we have an edge that connects a vertex v to a vertex w, can be directed or undirected edge, this edge is going to constrain the programs at vertex v and at vertex w to a convex constraint, and the weight of the edge is going to be a convex function of the continuous variables. So this is essentially a data structure. You can think of this as a data structure. And the question is, what kind of optimization problems can you pose over these graphs? And essentially, any combinatorial optimization problem that you can formulate over an ordinary weighted graph can be generalized with GCS. Take, for example, the classical shortest path problem, where you seek a path from a source vertex to a target vertex of minimum weight. That's a purely discrete combinatorial optimization problem. In the GCS version, you get a mixed discrete and continuous optimization problem. The discrete component comes still from finding a discrete path to the graph that goes from source to target. But once you select the path, the cost of that path depends on the underlying choice of the continuous variables that you make. So, for example, if you decide to go from the source to the target, to these two edges here that in the problem are over in green, then in order to decide the cost of this path, you have to optimize the continuous variables paired with the vertices along the path. And you need to satisfy the edge constraints, and you need to pay for the edge costs. Okay, so you get this nice kind of combination of discrete graph problems and continuous convex optimization. The same idea extends to other classical combinatorial optimization problems, like traveling salesman is naturally generalized to a GCS, as well as minimum spanning trees, but facility location, bipartite matching, your favorite combinatorial optimization problem over a weighted graph. So if we want to try to be a little bit more precise mathematically, you can formulate an optimization problem over an ordinary weighted graph, as shown here on the top right. We are given a set, calligraphic H, of admissible subgraphs. This can be paths in your graph for the shortest path problem, rules for the TSP, and so on. Among this list of admissible subgraphs, you are asked to select one, and the one you want to select is the one with the minimum weight. The weight of the subgraph is the sum of the weights of the vertices and the edges in the subgraph, right? So this is the combinatorial optimization problem that we start with, and this is the generalization over a GCS. We're still looking for a subgraph, H, in the set of admissible subgraphs, but depending on the subgraph that we select, we activate convex constraints, these ones that are paired with the vertices of the subgraph, and we activate convex constraints that are paired with the edges of the subgraph. The cost of the subgraph is still the sum of the cost of the vertices and the edges, but this time they're not even scalars, they are convex functions of the continuous values. Okay, so you can imagine that a variety of practically relevant problems can be formulated as these, as some sort of GCS problem. I come from a robotics background, and we have applied this kind of machinery in a wide variety of robotics problems. For example, humanoid footstep planning. You have a humanoid, and you need to select the areas where the humanoid is going to place its feet in order to arrive to a certain goal. Motion planning. I'm going to describe how a motion planning problem, so trajectory optimization kind of problem, can be formulated as a GCS problem in a second, both for robot arms, and then we have also got some UAV-like problems, then controllable grid systems, but also problems in computational geometry, or scheduling, a lot of it. So I would like to take a few minutes to try to give you a sense, at least, of how these GCS problems are solved. So let's start by kind of setting the expectations, right? So if you analyze most of these problems, they are NP-happy. They are computationally problems. So we don't expect to be able to reformulate them exactly as convex optimization problems, right? So what is essentially the next best thing that we can do is to formulate them as mixed integer convex programs that, as we have learned earlier today, can be solved at CVXPY. So what is a mixed integer convex program? It's an optimization problem where we have an objective function f that is convex, a constraint set x that is convex. Some of the variables are continuous, x, and some of the variables are, for example, integer, discrete, y. So a couple of important facts about these problems. They are computationally hard problems. So in the worst case, your solver will take exponential time to solve them. But there are basic algorithms that can solve them, that can solve to global optimality any mixed integer convex problem. These are kind of tension bound techniques. Secondly, in some cases, we are able to kind of fight this worst case exponential runtime by designing mixed integer convex programs that are efficient. What makes a mixed integer convex program in MIC efficient is the concept of the convex relaxation of the problem. So you can take this problem that I've shown here. The only main difficulty in this problem is that some of the variables are discrete, are integer. If those variables were actually real valued, then you would have a convex problem. That convex problem is called the convex relaxation of the problem that you can solve quickly to get an approximate solution of the MIC. If that approximate solution, if that convex relaxation is a good approximation of the original problem, then through a single convex program, you typically can get a very good guess for the optimal solution of the combinatorially hard problem. Of course, it's important to design MICPs that have these tight convex relaxations, but also are not too large in size. They don't have too many variables. So how do we do that for our GCS problem? We will do that in 3 steps. I will give you the highlights, since the details are a bit tedious maybe. We start from an integer programming formulation of the original discrete problem, which we then translate into a mixed integer but non-convex formulation for the GCS problem, which we then convexify into a mixed integer convex formulation for the GCS problem. And again, the details are a bit involved, so I will just give you some high-level highlights. So the first step is we start from the purely discrete combinatorial optimization problem. We've discussed this before. We want to select a subgraph H within a list of admissible subgraphs. It can be the path in a graph, the tools, etc., etc. We want to find a subgraph of minimum weight, where the weight is the sum of the weights of the vertices and the edges. In this form, of course, this problem is kind of not suitable for a computer because it really depends on how you describe this set of admissible subgraphs, right? If it's just a list, that list is going to be enormous. You cannot just go through one subgraph at a time and evaluate it. So how do you solve these problems as optimization problems? In practice, you simply parameterize a subgraph using binary variables. You can use what's called the incidence vector of a subgraph. So if you're given a graph G, you can have a binary variable for every vertex and every edge in the graph. The binary is 1 if the corresponding vertex or edge is selected in the subgraph, and the binary is 0 otherwise. It's kind of a one binary encoding essentially of the subgraph. So essentially, this allows you to map this list of admissible subgraphs into some high-dimensional space where you have one coordinate for every vertex and one coordinate for every edge. And subgraphs are potentially vertices of the hyperfield in the space. If you can find a nice convex set, typically a polytope, that separates the points in this high-dimensional space that represent admissible subgraphs from the one that represent inadmissible subgraphs, then you have kind of a computationally tractable optimization. And the good news is that for essentially any optimization problem, standard combinatorial optimization problem, this polytope is linear inequality satisfied, standard terms. Stepping back, essentially, we have our combinatorial optimization problem that can be reformulated as an integer linear problem, where we are optimizing over this variable y, which is the incidence vector of the graph, this vector with a 0, 1 variable for every vertex in the graph. This needs to satisfy some linear constraints defined by the polytope y, and you have a convex linear objective function that tells you the cost of the subgraph depending on the binary variables. You just multiply every binary variable by the corresponding weight. When the binary is 1, you pay the price of including the corresponding vertex. So these are an extremely well-studied class of integer linear programs, and studied for almost a century now. Maybe a century is too much, half a century. And some of them are actually incredibly efficient. For example, for the shortest path, the classical ILP integer linear programming formulation is actually known to have exact convex relaxation. So for that specific problem, we can just throw out of the window the constraint that the variables are binary, the convex relaxation will be exact. So you can solve it in a fractal set. So the next question is, now that we have this nice binary encoding of a subgraph, how can we use these binary variables in our GCS data structure to turn on and on the convex pieces of our GCS problem? So actually, the solution is pretty elegant. It's based, for whom of you have taken Stephen's class, on perspective transformations or homogenizations, they have mentioned. I'll try to give you a crash course. But imagine you have a constraint of the form x is in calligraphic x. You want this constraint to be enforced if the binary variable is 1, and you want no constraint to be enforced if the binary variable is 0. Right? How can you try to do this in a convex fashion? So the first attempt would look something like this, and it would actually not be too bad. you would multiply the constraint on both sides by the binary vector. On the left, you get the binary times the vector. On the right, you get the binary times the set. When the binary is 1, you get again that the vector is in the set. And that's true. When the binary is 0, on the left, you get the 0 vector. On the right, you get 0 times the set. It's a set that contains only the origin. So 0 is in the origin, always satisfied. You get very nice kind of on and off behavior using this concept. Let me do an extra step. Let me introduce a variable z that represents the product of these two variables, 1 and x. So now the variable z lives in the product of y of the set. It's equal to the product. The reason to do so is that now the constraint on the left is convex. When you have a convex set and you multiply it by a non-negative scaling factor, you get a convex cone. So that's a nice constraint that we can deal with. The one on the right, on the other hand, is a bilinear constraint that is less easy to deal with. But there are kind of standard approaches in the combinatorial optimization literature to deal with this kind of techniques. These kind of constraints, we have developed essentially a variant of whom of you knows the Lova-Schreiber procedure for 0-1. So it's kind of we have worked out a variant of that just uses convexity and not kind of a polyhedral structure. A cool thing that I've learned actually by digging in the CVXPY code base is that constraints of that form, where a variable is a non-negative scaling of a convex set, can be extremely efficient, easily enforced if the set is standard for the set is just multiplying the offset term by a binary variable, you get your perspective set. That's actually also explained from this perspective. So this essentially is what the amount of technical details I would like to give you about how we solve these problems. The good news is that we get these mixed integer complex programs at the end of the day that have few decision variables. They have essentially linear size in the graph size and the size of the optimization problems at the GCS vertices. And also the relaxation, most importantly, the relaxation of these mixed integer programs tends to be pretty good empirical, pretty tight optimization, convex relaxation. Most of the times, if you start with a combinatorial optimization problem that has a good integer linear programming formulation, that goodness is inherited by our mixed integer. So we have some marquee results, but they are more kind of curiosity than like really practice. And again, let me mention that these are technical details that the users of our libraries not kind of doesn't have to deal with. I like to think of these GCS data structures as follows. I would like the users to look at their problems, think what's the graph underlying this problem, what are the convex sets, what are the continuous variables, assemble this graph, then this graph is sent to us. We do all the mixed integer programming technicalities, we communicate with the CVXPY back and forth, and we return the solution, solve it. The user is kind of protected from the level of problem. Let me just give you a few examples and then a quick tour of GCSOPT. As an example, let me just walk you through this kind of cool-looking trajectory optimization problem. So here we have an archipelago with many islands in green, and we have a drone or a helicopter that is powered by solar energy that needs supply from the island in the bottom left to the island in the top right. At the top, you have the optimal trajectory of the drone. At the bottom, you have the energy, the battery level as a function of time. When the helicopter is flying, the battery goes down. Then the helicopter can take a break in an island, they charge the battery, to fly again. Of course, it cannot fly straight from the first to the last island because it doesn't. Right. And this is nicely formulated as a shortest path problem in GCS. You add one vertex to your GCS for every island. The variables, the continuous variables associated with every vertex are where you decide to land with your helicopter, in case you want to take a recharging rate in the island, and also the battery levels before and after the break. Then you have constraints on the vertices that relate the battery levels and the recharge time, and you pay a price that is equal to the recharge time every time you open them. Similarly, edges have link every two islands that are close enough. So edges essentially represent flights between islands, and the constraints on the edges link the flight time with the battery consumption, takeoff and landing position, etc. And again, the cost is for every edge, how much time you can fly. So the overall problem is arriving from the bottom left to the top right with the minimum time. So this is formulated in 20, 30 lines of code with GCSOPT. It can be solved. The optimal flight time is about 30.01 seconds. The MICP solve time is not crazy. It's 24 seconds. The issue is really, somebody discussed it before, that most of the solvers, this turns out to be a mixed integer second order phone program, and most of the solvers deals with these problems by successive kind of linearizations, and you see a lot of those when you try to solve this problem. But the cool thing is that if you just solve the convex relaxation of this problem, which is a second order program that's solved in about 0.4 seconds, then you get a lower bound on the optimal value that is essentially 5. So the convex relaxation of this problem is very important. I'm a bit behind with the time, so let me go quickly to the other examples. Here we had a bunch of other examples of different GCS problems that are not the shortest path problem. On the top left, for example, you have a school bus that has picked up a bunch of kids. If the kids were at fixed location, this would be a standard TSP problem. And now you also have the variable that the kids can move a bit around in order to reduce the total trip, the total length of the tour of the bus. And so you want to optimize this discrete continuous problem with TSP in DCS. Another problem here, you have a robot link. Here it is simple to be that is triangulated. When you do collision detection in robotics, triangulations are expensive to evaluate, so you want simple geometries that contain the links of your robot, and you can formulate the problem of finding the minimum volume collection of spheres that contain certain triangular mesh. That's a facility location problem in GCS, so using that line. And then other complicated problems in camera surveillance, inspections. Another full problem that comes from robotics that is naturally formulated as a GCS problem is motion planning around obstacles. Imagine you want to connect these 2 points, the starting point and the target point, with a minimum length trajectory that avoids the obstacles ahead. Imagine also that somebody gives you a nice kind of convex decomposition of the space that is not occupied by the obstacle. Right? Now you can construct a graph where you have a node vertex for every set in the decomposition. The continuous variables in your problem are where you enter and where you leave every convex set, and you assume that you travel along straight lines so that you don't leave the convex sets. Then you have edges that connect these convex regions and say, if you move from one region to the next, then you better have that the final point in the first region is equal to the first point in the second region, that you have continuity of your trajectory. And then every time you visit the vertex, you pay a price that is equal to the length of the distance of the 2 points between the set. So you pay the price of the length of the path between the set. So, and this also extends to move trajectories with polygons. But so motion planning, provided that you have this convex decomposition of the free space, is naturally formulated as a GCS problem. We tested it on very non-convex looking problems. We actually thought, what is the most non-convex looking motion planning problem we can come up with, and find a minimum length trajectory to a maze, and actually we can also solve minimum time problems. And these are actually both solved through a single shot convex relaxation. We solve the convex relaxation. You have allowed the variables to be between 0 and 1, and after they not either 0 or 1, all of them. So you have a lower and an upper bound. You have found a globally optimal solution to a convex problem. We have tested this on more complicated trajectory optimization problems, for example, drone flight. Here is an histogram of the relaxation gap. In all the instances, the gap between the relaxation and the MICT cost is lower than 20%. In 50% of the instances, the relaxation is exact. And if you do a little bit of rounding, most of it is recovered cheaply globally. Here we have motion planning problems in much higher dimensional spaces. Here you have two robot arms, 7 degrees of freedom each. So you are planning trajectories in 14 dimensions in the ground space. We have complicated algorithms that can try to decompose these high-dimensional space into convex sets, but then we can run our machine learning. Here we are solving only a convex relaxation plus a little bit of rounding. In this last task, for example, we're optimizing the trajectory of the arms, the order and the timing of the peaks in the plane in order to minimize the overall execution time given the physical limits. Maybe a minute, I can try to give you a very quick highlight of the library, GCSOPT. Let me just guide you through a toy example. We want to find the shortest path in this GCS. The edges in the GCS are these gray arrows. We want to find the shortest path from the bottom left to the top right, and we are only allowed to hope in this series, right? How do we code this up? First, you need to install GCSOPT. It's pretty installable. Then you need to import in your Python code both GCSOPT and CVXPY. Here a bunch of numerical parameters. Then you can initialize a graph of convex sets, as shown in here. In this case, we have a directed one, so that's true. We iterate through this grid for all i's, for all j's. This is the syntax to add a vertex. Add vertex, nothing surprising. You need to name a vertex. You can add a variable, the continuous variable for the vertex, and then you can add constraints. And the cool thing is that to add constraints, you can use any CVXPY function. You essentially have a CVXPY program for everything. Then you can do the same for the edges. You iterate over all possible edges. You get the variables back. You add an edge that connects the two vertices. So then you get the variables back, and then you add the cost using CVXPY syntax. Then you can say, this is my source, this is my target, solve the shortest path, and all the variables in a kind of a CVXPY style are populated with the optimal value, none if it's not used for the GCSOPT solution. And if you want to plot this thing on the left, 4 lines of code. Additional features, you have this basic interface to define and manage graphs. Convex sets and functions, as I said, are specified using CVXPY, so all the CVXPY atoms and functions can be used. CVXPY is also used to communicate with the solvers. So if CVXPY has a new solver, you automatically have it. Here are a bunch of solvers, commercial ones, open source ones, including the one presented this morning. And also let me mention that, as I said, just solving the convex relaxation and some basic roundings is actually effective for many of these problems without the mixing. Thank you very much. This is the link to the code, and these are some papers that you might get.
There's one question in chat that we'll watch. Somebody was asking about how this would apply to Marcucci or MCMC.
It does apply. Yes, if you have, I mean, you need this structure like many the traditional Markov chains. We have kind of this. If you have continuous states and you have this graph structure, then this machinery just applies. We do have actually some examples about optimal control, not really from a Markov chain perspective, more from a traditional kind of NPC perspective. Actually, all the best known mixed integer formulations for a hybrid model predictive control can be seen to be a special case of this formulation for DCS problem. Actually, that's the group here at Stanford of the paper that can be that specifically mixed integer formulation using perspective stuff can be obtained through GCS that by putting multiple layers. Every layer is a time step. Every layer is a bunch of nodes, which one for the different node. Thank you so much.
So we are now going to break for lunch. We'll resume at 1:15, 1:15 Pacific for those of you who are remote, and look forward to seeing everyone soon. Yes, so it'll be the same Zoom link. Yeah, you're welcome to stay on, and we'll just have this place muted. But otherwise, you're welcome to log out and come back in an hour. Thank you so much.